Now, for the past few lectures, we've been talking about parametric tests. Now, parametric tests, again, are statistical tests we use when the normal distribution or a certain distribution in a dataset is specified. However, there would be cases and researches and papers where we're going to encounter datasets that have no specified distribution. So the solution to that is that we get to use non-parametric tests. Now, non-parametric tests are also test statistics that have the same functions as our parametric tests. However, one key feature of non-parametric tests is that they don't have a specified distribution. Okay, so they would be a lot less strict when it comes to the distribution of data. However, they still do have its assumptions, or they still do have their assumptions. For instance, we have to have sometimes independence of observations. Sometimes we need to have um, dependence or paired observations. And sometimes we need to have a specified scale of measurement with our data. But anyways, let's talk more about non-parametric tests. Once again, non-parametric tests do not require a specified distribution, meaning that your dataset could be ordinal, or interval, or ratio. Okay, so what we mean by a specified distribution is that you don't need a certain um, shape of your curve for these tests to run. Now, a few examples of these non-parametric tests include your Kruskal-Wallis H test, which is your non-parametric equivalent to our analysis of variance. So, our Kruskal-Wallis H test, for instance, requires no specified distribution, and that would mean that this test is heavily dependent on ranks, as we'll learn more about later. Next, you have your Friedman test. This Friedman test is basically just your ANOVA, but this is for repeated observations. Okay, so we'll learn more about that again later. Now, this is not specifically like your ANOVA, but your Friedman test is a test of repeated measures that have measures exceeding 3 or more. Okay, so we know that when we have repeated measures, we usually run a paired t-test, but if you have 3 or more observations or repeated measures in a certain population, then a Friedman test would be more applicable. Then you have your chi-square test. Your chi-square test has many functions. It could function as a test of independence. It could also function as a test of homogeneity. And it could also function as a test of goodness of fit. So it has a lot of functions, but thankfully these functions are only applicable based on the dataset and the hypothesis that we're testing. And despite having many different functions, it only has one formula. Okay, so it's quite easy and um, easy to remember. Lastly, we have Spearman rank. This is sometimes referred to as your Spearman rank order test or your Spearman row. So your Spearman rank test is a test of correlation that requires a certain paired observation. So a common use of this Spearman rank test would be, for instance, you want to see if students, or rather if study time affects scores. Okay, so that would be one application of our Spearman rank test. Now, notice that our study time refers to one student as one student, and the score would be reflected or would be done by one student as well. So that means that you have a paired observation. You have the study time of your student 1 and the score of your student 1, and so on and so forth, going to student 2, 3, 4, 5, 6, 7, and so on and so forth. So these non-parametric tests, again, do not require a specified distribution, but they do have certain assumptions per test. So let's start discussing them all. starting with our Kruskal-Wallis H test. Now, like I mentioned earlier, your Kruskal-Wallis H test is a non-parametric test of difference that is basically the equivalent of our analysis of variance, or the non-parametric test that is equivalent to our ANOVA. Now, this is used when, take note of the assumptions of this test, your data is in the ordinal or continuous scale. So it could be either ordinal, interval, or ratio. Now, distribution of data is not a factor given that this is a non-parametric test, and there should be two or more independent categorical groups with observations that are independent from each other, so much like ANOVA. So just to elaborate on that further, you have to have two or more independent groups that are independent of each other, meaning that they do not affect each other, and you have to have observations that do not affect the other observations for each group. So there is independence of observations. Okay, so here is the formula for your Kruskal-Wallis H test. Now, here is the formula for your Kruskal-Wallis H test, and it's quite simple because we have constants on the formula. So you have 12. Again, this is a constant, meaning for every time you use the test, this is not going to change. And you have 3. Okay, so the formula is H, referring to our Kruskal-Wallis test statistic, is equal to 12 divided by n times the quantity of n plus 1 times the summation of the factor of R1 or Ri squared divided by Ni. So this, in fact, I think is the first time that we're going to encounter ranks in our testing. So ranks is going to be explained later, and actually the best way to explain that is through an example. So I'll show you an example later, but going back to the formula, you have to subtract 3 times the quantity of n plus 1. Okay, so very simple formula. No? So the only variable you have to compute for is this part. So let's get into the example. Okay, so a researcher would like to find out if there is a significant difference among 3 groups of propellant burn rates in a missile system. So we have to test this hypothesis at 5% alpha. Now, we have to, of course, apply the steps in statistical hypothesis testing. So first one is we have to analyze the problem, identify all the information that is relevant to our testing. So let's try to do that. Now, we're looking for significant difference, so we're going to be testing for difference. We have 3 separate groups. We're testing propellant burn rates, and we're testing it at 5% alpha. Okay, so another thing that's not given or not specified in our example statement is n. But if you look at the data set, all you have to do to get n is to count the number of observations. So let's do that. N is equal to, for group 1, you have 5. For group 2, you have 6. For group 3, you have 1, 2, 3, 4, 5, 6, 7, 8. You have 8 groups. Then n would be equal to 19. Okay, so now we have all the information we need for us to proceed with our computations. So we have to next formulate our hypothesis. So therefore, when we formulate our hypothesis, I'm just going to formulate the null. There is no significant difference between, or among, sorry, since we're talking about 3 groups, among the propellant burn rates. And to convert that to our mathematical symbols, you simply have to put mu1 is equal to mu2, which is equal to mu3. Okay, so simple as that. And since we're doing three separate groups, when we determine the tails of the test, this would most likely be a 2-tailed test. Now, for non-parametric tests, you don't necessarily have to put the graph, but of course, I would prefer you to include the bell-shaped curve. Now, since we're not assuming normal distribution, the shape of the curve really does not matter. What matters is that we can identify the tails of the test. By the way, um, we have to compute for the degrees of freedom before I forget. So degrees of freedom is h minus 1. H refers to the number of groups. Okay, so we need the degrees of freedom so that we can be able to identify the critical value. Which in this case, by the way, h minus 1, we have 3 groups. This is 1, 2, and 3. So your h is 3. So our degrees of freedom is 3 minus 1, that's 2. And using the degrees of freedom in the table of critical values for Kruskal-Wallis and chi-square, we get a critical value of 5.991. Okay, so let's move on to the next step, which is to compute. Now, computation is quite simple. What makes it a bit tiresome and, well, heavy in workload is the ranking of our different observations. Now, let's go to step 1, which is, again, ranking. So rank the data in ascending order from lowest to highest. For Kruskal-Wallis, this is not applicable to all, um, side note lang, no? This is not applicable to all non-parametric tests that require ranking. For Kruskal-Wallis H test, you have to take all the observations and rank them in order. Okay. So you're going to take all the observations from lowest to highest and rank them in a certain order. In this case, we have 16.7 as the lowest rank and 24.0 as the highest. So therefore, 16.7 is given rank 1 and 24.0 is given rank 19. Now notice that we have two different, or rather, variables that are ranked as 2.5 and 2.5. So for these cases, we're going to rank them. For instance, you have 17.3 twice, and this is because we have to rank them 2 and 3. But since they are the same value, we have to get the average of 2 and 3, which is 2.5. Same is applicable for repeated measures 18.9 and 18.9. This would be ranked 9 and 10. And this would be, we would get the average, which would turn out to be 9.5, and assign that rank to both of them. Now, just be careful, because when you assign a rank that is 2.5 for two separate observations, it's already assumed that they are taking rank 2 and 3. So therefore, our next rank should be 4. Same applies to our 18.9. Since we've assigned them 9.5 and 9.5, we took the average of 9 and 10. The next observation should be ranked 11. Okay, so kapag po meron kayong magkaparehong observation, 17.3 and 17.3 in this example, bibigyan po natin sila ng rank that is 2 and 3. But since they are the same observation, hindi natin pwedeng bigyan ng 2 and ng 3 respectively. We have to get the average of 2 and 3 and assign it to both. Okay, so that would be the ranking system and perhaps the most difficult part of the computation. So now that we've ranked them, we're going to assign or replace the observations with their independent ranks. Like this. Okay, so in the previous example, if you remember, 16.7 is ranked 1. So, i-assign natin ngayon si number 1 or si rank 1 doon sa place ni 16.7. Because what we're looking for is the summation of ranks per group. Now, hanapin natin si rank 19, which is, I believe, 24.0. So, i-assign din po natin si rank 19 in place of 24.0. So papalitan po natin yung independent observations with the rank that we've assigned them in the previous step. So, once we've done that, pwede na natin kunin yung summation ni R per group, which is 61.0 for group 1, 63.5 for group 2, and 65.5 for group 3. So, i-add lang po natin si ranks para makuha natin yung total rank ng isang grupo. Okay? So, once we've done that, pwede na tayong mag-input sa formula, or we could use the formula already. So, H is equal to 12. Again, this is a constant divided by N, which is 19, and times the quantity of N plus 1. I'm going to perform the operation already, so that's 20, 19 plus 1, times the summation of Ri squared. So that would be, I'm going to use a dot to avoid confusion. So that's 61.2. Sorry, 61 squared. Okay. Let me just delete. 61 squared divided by the number of observations in group 1, which is 5, plus 63.5 squared divided by the number of observations in group 2, which is 6, plus the total rank of group 3, which is 65.5 squared divided by the number of observations for group 3, which is 8. Okay? Medyo hindi nakasya, so I'm going to just remove this portion. I'm going to write it smaller. So H is equal to, I'm going to perform these operations. So that's 12 divided by 19 times 20 times the summation of 61 squared would give you 3,721 divided by 5 plus 4032.3 divided by 6 plus 65.5 squared, that's 4290.3 divided by 8 minus 3 times 20. And once we perform this operation, we're going to get an H score of 1.66. Okay, so this time we can conclude already. So our computed H stat is 1.66, and our CV, or critical value, sorry, is 5.991. So when it comes to non-parametric tests, actually, the conclusions are the same. So if your H is lower than your CV, then you have to accept the null. Same with your, if it's greater than your CV, then you would have to reject the null. Now, in this case, our H is 1.66 and our critical value is 5.991. 1.66 is definitely lower than 5.991, so therefore our conclusion would be to accept. Okay, so as simple as that. So to put that into writing, there is no significant difference among the propellant burn rates. Okay, so a lot more simpler than ANOVA. Ang matlabaho lang naman dito sa Kruskal-Wallis H test natin is the ranking system. So since you have to take all the observations from all the separate groups and rank them in ascending order, one being assigned to the lowest observation and the highest number being assigned to the highest observation, that would be the bulk of the work you're going to do in computing for Kruskal-Wallis. Next on the list is the Friedman test. Now, a Friedman test is just like your paired t-test. However, this is used in groups with observations that exceed 3 or more. So let's take it one by one. Friedman test is a non-parametric test of difference for scratch this. It's not 3 or more groups. It's just one group with 3 or more repeated measures. Okay, so for two repeated measures for one group, we use our paired t-test. But for this case, since we have 3 or more repeated measures, we employ the Friedman test. Now, the groups should contain random samples from the population, and the dependent variable should be measured in the ordinal or the continuous level. Okay, so now the formula for Friedman test, as you might notice, is quite similar to our Kruskal-Wallis H test. So you have your constants, 12 and 3, and you have your n, which is the total number of samples, and then you have your k, which is the number of measures, and that's about all the variables you need. We have rank over here as well, but as you will find out, our ranking system for the Friedman test is quite different from what we used in Kruskal-Wallis. Now, the best way to show you how to run the Friedman test is by an example. So here, a new experimental drug is being tested on 10 patients, and the study collected 3 different measurements of a certain cancer marker and has found to be was found to be encoded in the table. So to test the hypothesis that there is no significant difference among the cancer marker levels of 10 patients after treatment with the experimental drug. So first, of course, we have to analyze the problem. We are testing a new drug on 10 patients with 3 different measurements. So you have treatment 1, treatment 2, and treatment 3. Now we have to test the hypothesis, that there is no significant difference among the cancer marker levels of these 10 patients. As you might notice, alpha is not given, so we're going to assume 0.5 or 0.05 as our alpha. Okay, so the Friedman test requires us to get n, which we already know to be 10, and k, which we know to be 3. So that's k is equal to 3. And then we are left with r squared, which we're going to be solving later. So next, we formulate our hypothesis. Again, I'm going to do the shorthand mathematical version. U for treatment 1 is equal to mu for treatment 2 and is equal to mu for treatment 3. So that would be our null hypothesis. And then we have to determine the tails of the test. Again, this is a two-tailed test. Since we're only looking for difference, we're not looking if one improved or the cancer marker improved after the treatment. After that, all we have to do is compute. Now, again, I mentioned earlier that the ranking system for Friedman test is quite different from our Kruskal-Wallis H test. In fact, it might be a bit simpler. Okay, so let me explain. For our Friedman test, you have to get the rank of observations per patient and summate them by treatment. So, ang sabi daw po, we're going to rank them by patient. So, yung treatment 1, 2, and 3 po yung i-rank natin. And i-add na lang natin sila kapag nakuha na natin yung rankings. So, let's try that one by one. Let's start with patient number 1. Since 99 is the lowest, I'm going to assign rank number 1. And then for treatment number 1, or for patient number 1, ang sumunod po doon is 100, so that's 2. 120 is 3. And then you have 50, 65, 92. You have 36, 55, and 96. You have 41, 43, 65. You have 48, 65, 66, 15, 16, 65, 14, 18, 32, you have 14, 26, and 36. You have 36, 88, 98. You have 100, 125, and 150. Okay. So once na nakuha na po natin yung rankings ng ating treatments, all you have to do next is add them by treatment naman po. So sum of treatment 1, sum of treatment 2, and sum of treatment 3. So that would amount to, so 2 plus 1 plus 2 plus 3 plus 1, 1, 1, 2, 3, 3. That's 19. Then you have 1, 2, 3, 4, 5, 7, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. You have 20. And 1 plus 7 plus 6 is 7, 9, 12, 15, 18, 19, 20, and 21. Okay. So we have the variables we need. Let's write and substitute our formula. So you have Fm is equal to, again, 12 is a constant, divided by n, which is 10, times k, which is 3, times the quantity of 3 plus 1, times the sum of ranks, which is 19 squared plus 20 squared plus 21 squared minus 3 times n, again n is 10, times the quantity of k plus 1, that is 3 plus 1. Okay, so now all we have to do is perform the operations. So this whole term is going to amount to 0.1 times the quantity of the sum of our ranks, which is 361 plus 400 plus 441 minus this quantity would amount to 120. Okay. So if you perform that simple operation, you're going to get an Fm value of 0.2. Okay. So a lot simpler in terms of ranking. You're not going to have to arrange all the observations in a separate table. All you have to do is rank it by treatment. Okay. So next is that we have to conclude. Now, our conclusion is dependent on our critical value. So kanina, meron din tayong table of critical values for Kruskal-Wallis. For Friedman test naman, all you need is not the degrees of freedom, but the number of patients or the number of members or samples present in the group. So kung natatandaan natin, our sample is 10. Therefore, kukunin natin si 10, and our margin of error or alpha is 0.05. So ito na po yung kukunin natin. Get the intersection. And what we're going to end up with is 6.20. And since our computed FM stat is 0.2, alam natin that 0.2 is definitely lower than our 6.20 critical value. Therefore, our conclusion is to accept the null hypothesis. Okay? And to put that in writing, simply put, there is no significant difference among the cancer marker levels from treatment 1 to treatment 2. Okay, so that is how you run the Friedman test. Okay, so next in line, we're going to be talking about chi-square. So chi-square is a multifunction test. It could be used as a test of goodness of fit. It could be used as a test for homogeneity. and it could also be used as a test for independence. Now, chi-square, despite having three different functions, is relatively simple for the reason that it only uses one formula, and these tests, goodness of fit, homogeneity, and independence, are all dependent on the data that you're working on. So, let's talk about chi-square. Now, as the assumptions or the requirement of the test implies, your two variables should be measured at an ordinal or a nominal level. Your two variables should contain two or more categorical and independent groups. And this can be used again as a test of difference or association, including the goodness of fit, homogeneity, or independence. Now, looking at the formula for chi-square, by the way, this is a symbol we use for chi-square. It is simply the summation of the observed and the expected over the expected value. Okay, so I forgot to add the squared here. So, kailangan may squared pa po yan. Okay, so let's dive into our examples. So in this case, I'm going to show you two different examples. One for the goodness of fit and another for independence. And that's the reason for that is because independence and homogeneity is, well, presented with or used with the same sets of data. It only depends on the hypothesis on which you're going to use. But regardless, it's still the same process. So I'm just going to show you one example for homogeneity and independence. Let's start with this example. So a machine is supposed to mix nuts or peanuts, hazelnuts, cashews, and pecans at a ratio of 4, 3, 2, and 1. This is upon dispensing. However, when observed, the machine dispensed 270, 110, 80, and 40 of each nut respectively. Now, test the hypothesis that the machine is mixing nuts at a ratio of 4, 3, 2, 1 at 5% significance. Okay, so of course we have to analyze the problem first. We have to formulate our hypothesis, and of course we have to determine details of the test. Now, analyzing the problem, we know that we are supposed or expected to receive or see a ratio of 4, 3, 2, and 1. And our actual observation is 270, 110, 80, and 40 as encoded in this table below. And we have to test this hypothesis at 5% significance that our dispense or our actual observation is equal to our 4321. So therefore, our null hypothesis would be observed is equal to expected. Okay? So a chi-square test is most commonly a two-tailed test. So hindi po natin kadalasan ginagamit si chi-square test for a one-tailed function. So this is a two-tailed test. Okay? So now that we have all the information we need to perform our operations or to perform our test, let's move on to our computation. Okay, so when we start to compute, okay, so we have to first obtain our expected values. So we could not proceed with our computation without one of our variables. So to obtain our expected values, it's simply the formula of TV, which is total value, divided by total ratio times the ratio individual. So what we're going to do is to get the, for example, for peanuts, to get the expected values, it's simply total value, which is 500, divided by the total ratio, which is 10, times our ratio, which is 4. Okay, so that would get us a result or an expected value for peanuts of 200. Okay, again, for hazelnuts, let's start with 500, which is the total value, divided by 10, which is the total ratio, times the individual ratio of hazelnuts, which is 3, and that would give us 150. Okay, we have 100 over here and 50 over here. Okay, so very simple computation. Now, since we've already obtained all the variables we need to proceed with the computation, we can then proceed with our formula. So this is the summation of the quantity of the observed minus expected squared divided by expected. So I'm just going to write it down. So that would be 270 quantity of minus 200 squared divided by expected, which is 200, plus 110 minus 150 squared divided by 150 plus 80 minus 100 squared divided by 100 plus, that would be 40 minus 50 squared divided by 50. And that would give us a value of, or a chi-square value of 41.17. Okay, so as simple as that. Well, in fact, the most complicated portion of a chi-square test is getting the expected values. Okay, so now we move on to the conclusion. Now, our conclusion shares a table of critical values together with Kruskal-Wallis. So it's actually the Kruskal-Wallis chi-square table of critical values. Okay. So we compute the degrees of freedom for chi-square by the number of variables, or the number of dependent variables. In this case, we have 4 dependent variables, or independent variables rather. So looking at the table would give us a critical value of 7.815. And since our chi-square is 41.17, then we follow the same method for conclusions. If your chi-square, which is 41.17, is greater than our critical value, which is 7.815, then we have to reject the null hypothesis. So in this case, 41.17, which is our chi-square, is greater than our critical value. So therefore, we reject the null hypothesis. Okay? And that means, in this case, that the expected, or rather, the observations, the observed ratio of our not mixing machine is not 4, 3, 2, and 1. Okay, so that would be our conclusion. Another example, a researcher would like to know if smoking has an association with lung cancer. So the collected data of the researcher is shown below. Test the hypothesis at 1% significance that the presence of lung cancer is independent of smoking habits. Now, one thing that you have to note for table or contingency tables is that when we compute for degrees of freedom, which we're later going to use to obtain the critical value, we use the formula columns minus 1 times rows minus 1. In this case, we have 2 rows and we have 3 columns. So 2 minus 1 is 1, and 3 minus 1 is 2. So therefore, our degrees of freedom is 2. Okay, so analyzing the problem, we have all the data we need over here. These are our observed values. We, however, don't have our expected values yet, so we're going to have to compute for that. Next is to formulate your hypothesis. Then, simply put, our null hypothesis, the presence of lung cancer is not independent of smoking habits. Okay. Again, chi-square test is traditionally a two-tailed test. So we're going to use a two-tailed chi-square. Okay, so now we move on to our step 4, which is computation. Now, like with our chi-square test of goodness of fit, okay, so as was mentioned earlier, the most difficult portion of chi-square is computing for the expected values. Now, be that as it may, it's not really as difficult as it might sound. Now, in this case, to compute for our expected values, all you have to do is multiply your total per column, total per row, and divide it by our overall total. So for instance, let's have non-smokers, our expected non-smokers with cancer. So that would give us 69 times 100 divided by 180. Okay, and that would give us 38.33. Next is to compute for our no cancer. We're here. So what we're going to do is multiply 69 and 80 and divide that by 180. And that would give us 30.67. Same goes with our moderate smokers with cancer. So that's going to be 100 times 62 divided by 180. That would give us 34.44. Next, we have 62 times 80 divided by 180. That's going to give us 27.56. For heavy smokers with cancer, that would be 49 times 100 divided by 180. That would give us 27.22. Last, we have 49 again times 80 divided by 180, and that's going to give us 21.78. Okay, so now that we have our expected values, all we have to do now is compute. Okay, so our formula is the same. X squared or chi-square is equal to the summation of observed minus expected squared divided by expected. Okay, so we're going to have 6 terms. It's going to be relatively long. So that's 19 minus 38.33 squared divided by 38.33. So saan ko po kinuha yun? 19. Kinuha po natin dito. And yung 38.33 yung katapat po niya. Okay? So, continue on with that operation lang. I-add lang, or i-summate lang po natin. Our next term, in this case, would be 50 minus 30.67 squared divided by 30.67 plus that 42 minus 34.44 squared divided by 34.44. Okay? Ituloy-tuloy lang po natin yung method na yon. So again, kukunin lang po natin yung katapat niya. So for instance, I would label this A, and then A din po yung ima-minus nyo sa kanya. So B, B, C, yeah. So these are the terms that you're going to subtract and get the product of, or rather the result of. Okay? So i-mix and i-match lang po natin, wag pa lang i-mix. Sorry. Okay. So once you perform that operation, once you complete all the 6 terms you need, you're going to get a computation or computed chi-square of 37.13. Okay? So we can now then form our conclusion. Now, 37.13 is, well, I don't have the table right now, but I'm going to assume that it's greater than our critical value because this is a relatively high chi-square. So therefore, we have to reject our null hypothesis. Last for our non-parametric test is Spearman rank. So let's again start by discussing the assumptions of Spearman rank. Now, this is a non-parametric test of correlation, which is equivalent to our Pearson-R correlation, which would be our next week's topic. So Pearson-R correlation is, well, the parametric equivalent of our Spearman rank. This, again, is sometimes referred to as our Spearman rank order test, sometimes Spearman rho. Okay, so you might encounter those naming schemes for Spearman rank test. But for the purpose of our discussion, we're going to refer to it as Spearman rank. Now, the variables should be measured in an ordinal, interval, or ratio scale. And the variables, this is important, should have paired observations. And the relationship of the observations must be monotonic. What do we mean by monotonic? So it means that it has a linear correlation. So if one variable increases, let's say this is x and this is y, then the other should also increase. It could also be that if one variable increases, the other decreases. For as long as the relationship is monotonic, ibig sabihin, habang tumataas po yung isang variable natin, tumataas din po yung isa. Since they are paired observations, then that would be one of the basics of our correlation. Now, the formula is as follows. RS stands for Spearman rank, is equal to 1 minus 6 times the summation of the difference squared divided by n times n squared minus 1. Now, let's move on to our example. Now, the following are the scores of 12 students and the number of hours spent studying for a midterm examination in biostatistics. So calculate the correlation at 5% significance. Now, here we have hours and score. Analyzing the problem, you have 12 different students, so that would be an N of 12. Despite it having 24 separate observations, our sample size is only 12. Since, again, these are paired observations. Okay? Isang student lang po ang kada row natin. So that means our sample size is 12. Okay? So when we formulate our hypothesis, we simply put, there is no significant correlation between study time and the test score. Again, determining the tails of the test. Typically, this would be a two-tailed test. And now we have all the information we need for us to proceed with our computation. Again, sorry po, 5% significance or 0.05 alpha. So let's proceed with our computation. First step is to rank the variables in descending order, highest to lowest, and compute for the difference and difference squared. So in this case, i-rank lang po natin yung variables natin from highest to lowest. So yung pinakamataas na observation po, we're going to assign rank 1. And the next would be rank 2, and the lowest would be the last and final rank. Same rules din po tayo when it comes to ranking. If there are tied observations, kung may pareho po tayong observations like 85 and 85, we're going to rank them independently, but we're going to get the average of their ranks. So in this case, this would be rank 4 and 5. So binigyan po sila ng rank na 4.5 dahil in-average po natin yung ranks nila. Okay? So proceed with that, and all you have to do then is subtract or get the difference of the ranks. You're going to get your difference. You're going to square that difference, and you're going to add those difference squared. Okay? And we're going to get a sum of 17.5. So applying the formula would give us 1 minus 6 times the summation of d squared, that would be 17.5 divided by n, which is, pwede na pala nating isulat si n. So that would be 12 times 12 squared minus 1. Performing the operation, we're going to get 105 muna. 1 minus 105 divided by 1716. Further completing the operations, you're going to get a result of 0.94. Now we do have a table of critical values for our, for our Spearman rank, but just so you have an idea, I'm going to show you a table of levels of relationship. So this table represents our Spearman rank correlation. This would also be applicable for our Pearson R correlation. And this is the descriptive or the descriptive interpretation of your Pearson R or Spearman rank correlation. So since our result is 0.94, that would amount to a very high. Now take note, it could be positive or negative, so positive relationship. That means that you have a strong sense of, or strong statistical sense, that the more study hours you get would equal you a higher score. Okay, so mas matagal daw tayo mag-aaral, mas mataas po yung score na makukuha natin. That is what we mean by a very high positive relationship. Okay? So, just to give you an idea, our critical value from our Spearman rank table is 0.587. 0.587 is less than our computed Spearman rank, which is 0.94. So therefore, our null hypothesis is rejected. And that should coincide, of course, with our descriptive interpretation. Since our HO is rejected, which states that there is no correlation between study time or study hours and exam scores, this is rejected. So it makes sense, no? Kasi yung study hours nga natin, as indicated by our Spearman rank correlation, is correlated to a higher score. So mas mataas po yung study hours natin, mas mataas din yung score na makukuha natin. Pero ang sabi ni null hypothesis in its statement, it is not correlated. So si Spearman rank natin na test na ginawa proves or gives us statistical evidence that study hours, or the more you study, the higher your score is going to be. Okay? So it's a bit of a long lecture, it's a bit of a long topic. Non-parametric tests are a lot simpler in terms of its nature than our parametric tests, but hopefully we're able to keep up with our computations and with our assumptions. Okay? So once again, The difficulty lies within, first and foremost, identifying the test that you're going to use. So kung ano po yung test na gagamitin natin. And pangalawa, another difficulty is obtaining the variables where we need for the formula to work. No? And most of our variables require us to rank our data. So do take note and keep in mind the different rules in ranking our data. Iba-iba po kasi siya kay Spearman rank, kay Kruskal-Wallis, and kay Friedman test. So take note of how we rank our observations. That would be all for our non-parametric test. That would be the coverage of our midterms. So thank you and goodbye.